Thanks all the organizers and you for putting this up and having me. I'm very happy to be here. Now I put the quite general title into the program, Correlated Phases in SUN Symmetric Systems. But since we were motivated by Moiré, this is also a conference on Moiré, let me also add the subtitle. This is basically the system that got us thinking about this twisted AB stacked Moiré transition metal dichalcogenides. And I'm going to mention in a few slides why. But in the end, what we did is maybe more a general formalism, and that's why I want to talk more generally about SUN symmetric systems. And maybe I start with stating the obvious, that the correlated quantum systems we are now looking at usually have multiple degrees of freedom, and it's important that they have these multiple degrees of freedom. In our Moiré systems, these come from, for example, spin and valley, but if we are thinking more in the direction of solid-state systems, again, these could be orbital sublattice. Then, of course, SUN symmetry is maybe a fine-tuned point, but at least in these tunable systems like Moiré or cold atoms, it's conceivable that you can realize this, and there are suggestions that you do. And even in solid-state systems, nature sometimes conspires to give us this SUN symmetry. Then, of course, the question is why should you care about it? And just to give you a few examples, at least why I care about it is the effect on phases of correlated electrons. And a few examples where this comes in or leads to an interesting effect that have been discussed are here. For example, mod insulators and interesting spin orbital liquids. There's been suggestions that this SUN will support to induce spontaneous loop currents or Stagger flux orders. And for example, there can be novel types of pairing scenarios. If we then go more towards our Moiré systems, SUN symmetry, SU4 symmetry specifically, has been discussed in certain limits of graphene-based devices or as emergent symmetry in these systems, and there it's based on spin and valley. But as I said in the beginning, the system that concretely motivated us to look into this Moiré transition metal dichalcogenides, and more specifically the suggestions in this paper here, and two of the authors are also in the audience. And what's the proposal here is that if there's some mechanism how we can basically reduce or turn off interlayer hybridization, for example, through AB stacking, so 180-degree starting point, or some separating layer, that means layer remains a good quantum number, and then combined with the locked spin valley degrees of freedom in that system, it gives us an approximate SU4. And then more generally in Moiré transition metal dichalcogenides, at least in certain, for certain parameters of the Moiré potential, for certain twist angles, it was shown that you can realize triangular lattice models. So that would lead then to an SU4 symmetric triangular lattice Hubbard model if you put interactions in the simplest case. So this is what we wanted to study, at least in theory, but it was also realized experimentally in Cornell, this twisted AB stacked tungsten diselenide, and there are signatures of interesting insulating, correlated insulating phases at integer fillings. But even more generally, going away from SU4 in these Moiré TMDs, interesting correlated phases do not only appear at integer fillings, but also at Van Hove fillings. And here you see one example, and these Van Hove singularities that you have there are also tunable, for example, by displacement fields. So this is why we wanted to look into this SU4 triangular lattice Hubbard model, both from weak and strong coupling. Weak coupling meaning Van Hove scenario, strong coupling going into really strongly interacting Heisenberg model. But before going into this application, I actually want to present the mechanism or formalism we then developed more generally for SUN symmetric systems, which means I want to look into Fermi-liquid instabilities in these systems, where we worked out a Kohn-Luttinger-like mechanism for what I'm going to call unconventional charge orders. And then hopefully, I'm not sure if I'm going to get to the end time-wise. If not, we can discuss later. So let's directly start with that. Fermi-liquid instabilities, just to give you well-known examples. There's the Stoner instability, which would lead to spontaneous spin polarization. Maybe even more famous example would be the Cooper instability for superconductivity. And then going to a Van Hove scenario because of the large density of states. Maybe even with the nested Fermi surface, we expect competing orders, so a bit of a more complex situation. And then with this nesting, usually you would get spin density waves and surrounding pairing states within that scenario. Now, recently, several systems have emerged where actually the spin density wave is replaced by a charge density wave, and that charge density wave can be unconventional. And with that, I mean still an interaction-induced Fermi-liquid instabilities in the particle-hole channel. So we have this typical charge density wave, but it can have a finite angular momentum. And that means it gets a form factor like superconductivity, P wave, D wave, etc. If you transform this back to real space, you find that this does not lead to a simple, really modulation of the charge density itself, but instead, depending on the symmetry, the form factor, you will get loop currents or staggered flux phases, or alternatively bond density waves, for example, stripes. And this may be relevant or has been discussed, for example, in cargo maze, but even back then for cuprates, cold atoms, as well as Moiré systems, where, for example, we would also see stripes in this heterobilayer. Furthermore, what's interesting and what's been pointed out on the model level, if you think of triangular honeycomb or square lattice models, this large N in SUN seems to support the formation of these unconventional density waves. So this is what we wanted kind of to understand better. And for that, let me go into the formalism. I apologize for the quite technical slides. If you're not interested, you can wake up in like 2 slides. But basically, what you need to do to get such a Fermi-liquid instability, or one way you can get is you look at the renormalized effective interaction in your system. So the interaction, the particles really feel due to multiple scattering processes in a many-body system. And if that has a divergence, it means there's an instability in your system, and there are different ways, and it's complicated to calculate that effective interaction, but maybe the simplest way is to look into different channels separately, and that would give you self-consistent beta psi beta equations. And here I'm showing again the 2 maybe famous examples where you get such an instability. One is the Cooper channel, so this one amounts to the Cooper ladder, and then your effective interaction is of this form, and you see there can be a divergence and instability if the denominator vanishes, which means that we need an attractive interaction for this to happen, which is something we all know. We need attraction for superconductivity. If we look into the spin channel, which is in this case equivalent to the cross-particle hole channel, so we look at this interaction as function of the exchanged momentum. In that case, you get this effective renormalization, and you see here we can get an instability already with the Bayer repulsive interaction. For example, that would give you Stoner. So now let's go and do this for the systems I have in mind, large NF for SUN, and look into the charge channel. For large NF, the charge channel is equivalent to the drag particle hole, which means I look at this as function of transferred momentum. And then basically, we saw already in Paco's talk, this these corrections, these fluctuations will be the leading ones, because I can have any of my flavors here contributing. And this is actually something we all also know very well. It's the simple original RPA resummation and leads to screening. So you get this type of renormalized interaction, which means for repulsive U, the interaction is reduced and there's no instability. So similar to the Cooper case, actually you need an attraction to get such a charge instability. And then also in full analogy, the question is, where do you get that attraction from if you start with a repulsive electronic interaction? And so this is what we were thinking, and then also really, we just follow what's been done for pairing, and one way to do that is via a Kuhn-Luttinger-like approach, which would be a purely electronic mechanism to get this attraction. So I wanted to remind you of Kuhn-Luttinger mechanism, but actually Paco basically already did that for me. Let me still just mention it to set up the formalism. What was the ingenious idea of Kuhn and Luttinger is, if we look at the interaction in the pairing channel, instead of using the bare Coulomb repulsion, we use the one corrected by particle hole fluctuations. In diagrams, these would be just these diagrams. And because of that, adding these corrections, your interaction becomes momentum dependent, and that momentum dependence can develop an attraction in a higher angular momentum channel, and that's sufficient to get superconductivity in that channel for this higher angular momentum. What this means for the superconducting state is that the pair wave function vanishes if the two particles are at the same point, and in that way you can effectively avoid the even strong bare Coulomb repulsion. And now we do the same thing, just in the charge channel. So again, we look at our RPA screening diagrams, and now we correct the bare interaction by fluctuations, which now come from the crossed, so spin fluctuations, and pairing fluctuations, the particle-particle channel. So this would be these two diagrams. And then again, because of this, even if we start with bare constant Hubbard U, we get momentum dependence, and that can develop an attractive component, which then would give us this instability for one of these unconventional charge density waves. Okay, so now, if you want, you can wake up if you're not interested in the formalism. Now I'm going to go to the application. And we looked at this first for two models, square and triangular lattice, SUN models, which means we have, in our case, just nearest neighbor hopping. We control the filling and go to Van Hove filling, where we have nesting plus the Hubbard interaction. And you see the resulting eigenvalues here in the coupling in this charge channel as function of filling around Van Hove, which is here at 2 for the triangular lattice and at 0 for the square lattice. And in both cases, and I should say the instability will be determined by the most negative eigenvalue, so the most attractive angular momentum component. In both cases, you see that this is a P wave. So we get P wave charge density waves, and their momentum, their wave vector correspond, as you would expect, to the nesting wave vector in the two systems. Their critical temperature in this formalism is given by this, which is slightly enhanced compared to maybe the weak coupling scenario with constant density of states. First of all, because we have Van Hove, and then because we have nesting. These P-wave charge density waves, if you translate them back to real space, give you the following patterns. In the square lattice, based on symmetry, Px and Py must be degenerate. So there's a question, what's the linear combination that is formed in the ground state, which we haven't touched yet. I'm just giving you one example. If you have both of equal magnitude, you get such a stripe bond order. Going to the triangular lattice, The form factor itself is py, and it's unique. However, there you have 3 inequivalent nesting vectors, endpoints. So again, the ground state will be determined by the linear combination. And just to give you another example, if you take a single Q order, you get such a stripe bond density waves. So this could be one explanation for the stripes you see at 1/4 filling in triangular Moiré TMDs. Of course, since the situation I'm considering is at Van Hove, there's nesting, there will be competing orders, like spin density waves or pairing. And then the question is, if I'm not at super large n, can the charge density wave really win? And the first step in answering that question is simply comparing these single channel conditions for the instabilities. In the case that we have nesting, these polarization operators are actually of the same order, which means I just need to make the interaction in this charge channel large enough, and that I can do if my flavor number is large enough. And this kind of critical flavor number would be determined by the ratio of the effective coupling in the charge density wave channel and the other couplings. Okay, so this was the results for this Kohn-Lattinger, really pure Kohn-Lattinger-like mechanism, which means we correct just via one loop fluctuations. And then, of course, the question is, can we go higher? Can we include more fluctuations? And one thing to do here is, because we are close to a nested situation, spin fluctuations will be close to singular. So instead of taking just these one loop diagrams, we can do a spin fluctuation approach and sum the entire spin channel and use then this as an input for a charge channel. And doing that, working out the formulas, we find that the induced coupling here for the charge channel, the particle direct channel, is actually related to the coupling that you would get in the pairing channel doing the analogous thing, so spin fluctuation approach for pairing. The only difference is that you get a factor proportional to your angular moment, -1 to your angular momentum. So that means we can basically, at least for the coupling, for the systems where this has been studied, such a spin fluctuation approach, we can take the result and just transfer them to get the charge density wave coupling. There's a small thing you need to be aware of, because in the charge density wave channel, this polarization operator is not necessarily diagonal, and you need to do a bit more work. Good. And then another alternative, if we are already talking about spin fluctuations, is maybe going away from this well-defined weak coupling universal considerations and phenomenologically add a next nearest neighbor spin exchange, which may be induced by the stronger Hubbard interaction. Here just generalized to the SUN operators instead of SU2 spins. Such an interaction, for now I still want to consider it in the scenario where the bandwidth is larger than that interaction. And if you have such an interaction, it will be attractive for these uncorrelated charge density waves with higher angular momenta. But as you know, it's also attractive for spin orders or pairing. And then again, we need to check if the charge density waves win, and this leads to this more generalized condition where now also added the polarization operators, so the susceptibilities in the different channels. And you see again, if I just make this NF large enough, the charge density wave can win. In particular, in that case, you don't need nesting for them to win. You just need, you need to overcome the logarithm that you may have in the Cooper channel, for example. Okay, so then we looked at the instabilities of such an Hamiltonian, again applying it to square and triangular lattice as a starting point. And this was actually done before for the square lattice, and we just reproduced the results there. What you get is a dx squared minus y squared charge density waves, and that leads to such a staggered flux state, so loop current state in real space. Doing the same thing for the triangular lattice, we find something that at least was surprising to me, and that goes back actually just to the single particle physics of the triangular lattice. Namely, if you look into the polarization operator, so the particle holes have susceptibility, the bare particle holes have susceptibility, at different fillings, you'll find that the peak, so this is plotted here, the peak, which determines the wave vector of your instability, will jump from the nesting vector around Van Hove to a value along the gamma k direction that is close to k over 4. And this is, supposed to be presented here, this jump, as function of filling. This means if you put this in together with the attractive interaction in the charge channel, you will get a transition between two different charge density waves with different wave vectors, and we did not find such a thing on the square lattice. And this you see here, again, I'm plotting the eigenvalue, the most negative, the two most negative ones. Now it's function of filling, and you see indeed there's a switch, which one is more negative when this peak position changes, which means you get this transition from a wave vector m to a wave vector k over 4, around approximately k over 4. And well, then we also wanted to know if this is something we can get in maybe a more realistic setup, so not just for super large n, concretely for this SU4 case, triangular lattice, going back to our motivation of the twisted A-bisect TMDs. And if in that case, these charge density waves can still win against these other competing states. And for this, we did the functional renormalization group calculation, which allows us to calculate this effective coupling I was showing, but including the different channels on equal footing via such a differential equation. In particular, it includes the mutual feedback between all of these, if they suppress each other or not, or enhance each other. Furthermore, we made use of methodological developments of the past years, which allow us to have a really good momentum resolution, both for these form factors as well as the wave vectors of the density waves. Okay, and this is the result we get as function of filling, the critical temperature, as well as the type of order of this FRG calculation. Blue means a pairing instability, and orange means a charge density wave instability. And then here on the bottom, I'm showing the data that the FRG gives us for the form factors. So this is really data. And we, around nesting, around Van Hove filling, we do get what we would expect, a charge density wave with wave vector m, and the form factor is a dxy form factor. That was seen before. And also what was seen before is for example, Parquet renormalization group calculation. Also what was seen before are these d-wave pairing instabilities. And the new thing we found is this order here, which interrupts the pairing. So here we also find a charge density wave instability. Its wave vector is indeed k over 4, and it does have a d-wave form factor. Translating these charge density waves into real space, you get the following. The one that was discussed before, again, the d-wave charge density wave with wave vector m. You have single and multi-Q orders, and it leads to loop current states. And here I just want to mention, for example, this multi-Q order will give you an interaction-induced quantum anomalous Hall state. So it's another way of obtaining a Chern insulator at a fractional filling. The new state we found is d-wave charge density wave with Q with wave vector k over 4. Has both components, bond and loop current. orders, and you need to go to larger lattices to see this period K over 4. Yeah, and then for single and multi-Q, you get these nice kind of tilings of the triangular lattice. Good. Do I still have 5 minutes? With that, I'm done with this weak coupling scenario, and I want to switch gears to the strong coupling case of the same SU4 triangular lattice model. And in strong coupling, I really mean going to the Heisenberg description, where we have nearest neighbor Heisenberg interaction between these generalized spins, as well as the next nearest neighbor one and the displacement field that will discriminate between the 2 layers. This is interesting because there's strong frustration in that system, not simply geometric frustration from the triangular lattice, because I could satisfy this antiferromagnetic condition and having different flavors on each of the side of the lattice. However, I can replace each of the flavors by the 4th one and get the same ground state energy if I only have this nearest neighbor interaction. So there's a huge degeneracy on the classical level, and that's what gives you the frustration. Well, then we wanted to see what this leads to on the quantum level if you add the next nearest neighbor interaction and the field. And we did this using several methods. The first most easy thing to do is, of course, mean field. And then we get this phase diagram. The interesting thing is that as function of the field, we can tune between an SU4 limit and an SU2 limit. In the SU2 limit, the field is so large that you kind of only populate one of the layers. And in that case, we were considering this at a quarter filling. You go back to the half-filled triangular lattice, which has been studied extensively. And the phases we find here in between actually kind of smoothly interpolate between these 2 limits. We have a generalization of the 120-degree antiferromagnet, which we can explain leads to a ferromagnetic occupation in the other layer. And the stripes you get in the SU2 case go to a 4 sublattice state that is basically made of the combination of more than one stripe in different directions. Of course, as you know, the interesting thing maybe is about these systems is that there may be spin liquids, and we did not yet use a method that could tell us about them, but you can see if these orders are destroyed due to quantum fluctuations, for example, using linear flavor wave theory. So if you calculate the excitations, you'll find that there is a soft mode going here along the field that develops and becomes exactly flat. And that, will likely destroy your order. In that sense, these zero energy fluctuations survive from the classical level to the quantum level. So using this and recalculating the order parameter, we indeed find that there is a quantum disordered ground state where no, at least mean field order develops, and that happens here in this hedged green region. And interestingly, in the SU2 limit at least, this region coincides with the spin liquid region that people find in more advanced calculations like DMRG or Monte Carlo. There's also been such suggestions of putative spin liquid for the SU4 case, and maybe because we can also experimentally tune between these 2 limits, this will help us understand the spin liquids better. Then finally, we did an ED calculation also for this system, just for 12 sides, because we have this large flavor number. You can calculate the polarization as function of the field, as well as analyze the spectrum. And for antiferromagnets, there's something called the Anderson tower, where the lowest lying states of the spectrum should lie on a line. So in the regions where we had these antiferromagnetic states, we should get this as function of polarization and filling. And indeed, just to cut this short, what we find in ED is consistent with this phase diagram I showed earlier with the what we call strongly fluctuating phase, where we do not have an order. Okay, and that brings me actually to the end, to my conclusion. I hope I could show you that if you have these multiple electronic degrees of freedom, there are systems where we at least approximately realize an SUN symmetry, and that can have interesting effects on the phases of correlated electrons. We were concretely motivated by the transition metal dichalcogenides, and that's why we studied SU4 triangular lattice Hubbard models and weak and strong coupling. And I showed you that you can get interesting unconventional charge density waves, so loop current or bond orders, out of a Kohn-Latinger-like mechanism for the particle-hole channel. And in strong coupling, there's an interesting quantum disordered state that we want to understand better in future. Thank you.
So this D-wave CDW, is that specific for SU4, or could it occur for the SU2 case, or it just needs large N? Or?
Yeah, so the form factor can vary. We found for the two systems we studied, square lattice, triangular lattice, at least if you have the spin fluctuation approach, that it's D-wave, I guess because of the spin fluctuation for both square and triangular lattice. And it remains that we did look at higher, and it remains, at least on the square lattice, it remains dx squared minus y squared. Mm-hmm. On the triangular lattice, I think we did not find it at some point anymore in the FRG, but I think the reason is screening, and critical temperatures just go below our detection threshold.
Mm-hmm. So having these the larger number of flavors helps you stabilize some of these states which would not otherwise be there.
Yes, that's exactly the point, because of the large N. Where large, it's a question what is large, but because of that you can stabilize the charge orders.
Thanks.
So since you mentioned the Kohn-Latinger scenario, do you have speculations on where superconducting pairing might occur here, and whether SU4 versus SU2 might support that more?
Yeah, so we usually find the pairing, I showed this schematically, but it's actually also in this phase diagram. We find it flanking the kind of particle-hole order, which can be charge or spin around Van Hove, and then next to it, due to these fluctuations, particle-hole fluctuations, you get an unconventional superconductor. The new thing kind of is that you can also, via the same mechanism, get an attraction in the charge channel. But as you point out, you need to ask if that competes with superconductivity. It does, and yeah, we find that superconductivity or pairing instability win in most of the phase diagram.
Thank you very much, Laura. So what can you say about the nature of the spin liquid that you are finding here, and especially how does it go? It flows from the SU2 to SU4?
Yeah, so basically I can't say anything because we didn't study that. This is exactly what we want to do. I guess we know from other studies for the SU2 case, it's the Dirac spin liquid, but then the question is how does it generalize to the other degrees of freedom that we have.
So how do you want to do that? Do you want to calculate excitations, or because this is now done with this Gutzwiller type of wave function, right? So you are at t equals 0. So
what we are doing now is just Pardon constructions and see what happens there. And then, of course, I've been talking to people who know how to do DMRG, but this is not my field of expertise. So that might be, I think it's expensive because you break the SU4, but maybe it's possible.
Okay, thank you.
Thank you for a great talk. If the large number of flavors is stabilizing charge density wave that of this, because usually they don't win, right?
Right.
So then by reducing the number of flavors, maybe you can promote superconductivity. I don't know, some magnetic ordering, valley polarization, spin orbit coupling. These things should promote superconductivity.
Yes,
right?
yes, and so they do. Actually, I should say the superconductivity is not that much affected in the sense that we
But you
get the
suppress
pairing
the-
instability both for SU2 as well as SU4.
But you're suppressing the charge density wave, which is competing.
Exactly, I'm
Yeah.
suppressing the charge density.
Yeah. So,
Yeah, and the thing that's more affected is the spin density wave, because that one loses.
Any other question? All right. Thank you, Laura.